Welcome my friends, welcome to my next lecture. Now today's lecture, my plan is to talk about the concept of what is called antiderivatives. Then I will talk about more on path independency. Then you will have what is called Cauchy's theorem on Cauchy's integral formula. Then we will have Cauchy's estimate as an applications of Cauchy's theorem. We will have Cauchy's estimate, Liouville's theorem and Morera's theorem. So these are the very fundamental theorem in complex analysis. So this is kind of the materials for week 4. Let me see how far I can complete. Now if you remember in my last lecture I discussed in fact, I have proved what is called one of the fundamental theorem in complex analysis, mainly Cauchy-Goussat theorem and the proof, and then I have discussed little bit about path independency. Now you will see the notions of antiderivatives and path independency, they are interrelated along with Cauchy-Goussat theorem. So for today's lecture I will start with antiderivatives and slowly I will connect the path independency, existence of antiderivatives and Cauchy-Goussat theorem. So that's my plan for today's lecture. So this is like kind of concepts I would like to discuss in week 4, but maybe not all, maybe most of the concepts I'll discuss, maybe like Morera's theorem, maybe this one, maybe I'll go for the week 5. Or maybe Gauss mean value theorem, that I'll discuss in week 5. But week 4 maybe I'll start with antiderivatives, then we'll have what is called path independence, then Cauchy-Goussat theorem, of course I have discussed for simply connected domain, then I will have the statement in the multiply connected domain, then I'll discuss what is called Cauchy's integral formula, then Cauchy's integral formula for nth derivative, then couple of consequences, and couple of consequences means we'll have like what is called Cauchy's estimate and Liouville's theorem, maybe Gauss mean value theorem and Morera's theorem I will go for the week 5. Okay, so that's for kind of week 4 plan. Now let me just start with the concept what is called antiderivative and primitive. Now these notions you are familiar with in real analysis also. So if what is the definition of primitive or antiderivative? So if I have a function, say f is continuous function from some say interval a b to r, a function f possesses a primitive or it will possesses an antiderivative. What does it mean? That means there should exist another function, let it be capital F, such that if I take the derivative of capital F, it should exactly equal to your small f that you started with. If these things happen, then I will say that small f possesses antiderivative or primitive, or capital F is the primitive or antiderivative of my functions f. So it's the same definitions. Now in the context of complex valued functions I can extend parallelly. What is the definitions? So an antiderivative or primitive, okay, of a continuous functions f in a domain D. So you have a continuous functions in a domain D is a functions capital F, okay, like in the real analysis you know, such that if I take the derivative of capital F, it is exactly equal to my small f, and that's so true for all z in D, okay. So if these things happen, then I will say that small f possesses what is called primitive or antiderivative, or I can say that capital F is the antiderivative or primitive of my small f, okay. So this is the definitions. So that means if I have a continuous function possesses a antiderivative or primitive, I will say that if there exists a function capital F on the domain D where my function small f is defined, such that if I take the derivative of capital F, it is exactly equal to my small f, and that is true for all z in my domain D. So one of the observation is that the capital F I am getting, if I say that this capital F is actually analytic functions I am getting, so then since capital F prime is small f, then one can conclude that small f is also analytic. Now this is like, you can later on I will prove that if my function is analytic, then it is infinitely many times differentiable, though I have not proved it. When I will have what is called Cauchy's integral formula, there you will see the analyticity implies infinitely many times differentiable. So therefore if capital F, if I assume that my capital F, the antiderivative which I am having, and if it is suppose analytic, capital F, then it is infinitely many times differentiable. That means capital F prime, which is exactly equal to small f, that means small f is also infinitely many times differentiable, that means small f also analytic, okay. So this is special. So if I have antiderivative or primitive is analytic, then the given functions f which possesses antiderivative, that is also analytic functions. Second observation is that suppose you have two antiderivative for a given a function small f, then how the corresponding two antiderivatives or primitive, how they differ. Okay, it says that if I have capital F1 and capital F2 are two antiderivatives of a function small f in a domain D, then they differ by a constant. That means F1 minus F2 is exactly equal to k for all z is in D and k is a constant. So that is the antiderivative of a given function f is unique up to an additive complex constant. So therefore, given a function f, suppose you have two antiderivative exist, then they differ by a complex constant. Okay, you can prove it. So it's very easy. Okay, so now this is antiderivatives. So now what is the advantage of antiderivatives? Now you see, in my last lecture I was talking about like path independency. What is the meaning of path independency? Suppose you have a domain D, and suppose you have a function f which is analytic in a domain D, and suppose I am considering 2 points, say one is z1 and another is z2, right? Now then I am saying that okay, I have already discussed contour integrations. Now since my functions defined on my domain D, now if I take a contour, say let it be C1 starting from Z1 ending at Z2, then I already give a meaning of my contour integrations of f over my contour C1, right? That I have already discussed, fz dz, right? Now it will give you some value because f is analytic on D, that means in particular f is analytic on my contour C1, okay, and C1 then the corresponding what is called contour integration or line integral exists, and it will have some value. Now you can ask, okay, instead of contour C1, if I take another contour, let it be C2, right? Then you can have another contour integration C2 fz dz, right? Because the way I have defined, so that also give you the value. If I take another contour, say C3, you can also make sense of integration C3 fz dz. So all make sense, the contour integration and line integrations, and each of them will give you some value. Now the question is whether all the line integral over this contour will, of course it will exist because f is analytic there, but whether all the values are same. In other words, what I am trying to say is that whatever contour I will take starting from Z1 and ending at Z2, the corresponding contour integrations, whether it will give you the same value. That means whether the contour integrations is independent of the choice of the contour joining Z1 and ending Z2. So this kind of questions I have kind of already discussed in my what is called last lecture. Now antiderivative plays a crucial role here. And what is the crucial role? Look at the statement of the theorem. It says that suppose you have a continuous functions defined on the domain D, okay, perfectly all right, and suppose small f has an antiderivative, that means small f possesses, that means small f possesses an antiderivative, that means there exists a capital F defined on my domain D such that capital F prime is equal to F. Suppose these things happen, then look, then it says that then for any contour C lying in D starting from Z1 and ending at Z2, this contour integration or line integral is independent of the choice of my contour. That means it is path independence. So this is one of the sufficient conditions. So if I start with my function small f on some domain D, if I take any 2 points Z1 and Z2, and if I assume some extra condition, that means if my function small f possesses an antiderivative, then the contour integrations, that means whatever contour I can take starting from Z1 ending at Z2, the corresponding contour integrations is independent of the choice of the contour. That means it is path independence. So therefore existence of an antiderivative implies path independence. Later on you will see I will have another conditions when I can say that my function small f has an, or when small f has an antiderivative. If small f possesses an antiderivative, then of course the corresponding contour integration path independence. So the only problem will remain that if some conditions, if I say that yes, look, if these things happen, then small f always possesses a what is called antiderivative or primitive, then by this theorem I can say that then path independency automatically follows because of that one. Okay, so first let me just assume that small f possesses an antiderivative, then I will prove that it is independent of the choice of the contour. That means whatever contour I can take starting from Z1 ending at Z2, the corresponding contour integral exists and it will give you the same value. Okay, so proof. So this is the proof. So proof I already, if you the way I will discuss the proof, you will see it is nothing but the what is called applications of fundamental theorem in the real analysis that you know. Okay. So look, so what is that? So this is your theorem. How to prove it? So I will say that okay, take some C and I will say that whatever c will take, this of course this integral will exist because my function is continuous, this continuous integration will exist, and it will have the same value independent of the choice of the contour. Look, okay, so take a contour c, suppose c is a contour, okay. So now I have this my domain, my function is given, now I am considering one point z1, another point z2, and suppose you have a contour c, that's it, okay. So I am considering a contour starting at z1 ending at z2. Now since it is a contour, it will have a parameterization, so let gamma is the parameterizations of my contour c. So therefore you can say that z1 is equal to gamma of a and z2 is equal to gamma of b, right? That's perfectly alright. Now what is given? That small f possesses antiderivative, okay. That means small f has antiderivative or primitive. That means there exists a capital F such that f prime of z is small of fz, and this is given for all z in D. Suppose this is given. Now I want to calculate this, what is called contour integrations. Now if I calculate this contour integrations, now what is the definition of contour integrations? Because I already have a contour c and which will have a parameterizations gamma is given. So what is the definition? By definition, this is nothing but integrations a to b, f of gamma t, gamma prime t dt. That's the definitions of contour integrations, right? This is perfectly all right. Now the point is that since small f possesses antiderivative, so therefore this integration exactly equal to this. And why this is true? Just because of chain rule. Look, so capital F prime of z is equal to small f of z is given, okay, inside in D for all z. Now if I take C, which is a contour, that means what are the points on C? These are the points actually gamma t. So therefore you can say that, so I can say that, you can say that this will implies, so this is also true, so then this will implies f prime of z is equal to small fz for all z in C also, because C is inside the domain, right? And that means this will implies capital F prime of gamma t, which is same as small f of gamma t, and this is true for all t belongs to what? A to B, because gamma t are the points on C. So therefore capital F prime of gamma t is exactly equal to small f of gamma t, right, for all t inside the interval a to b. Now consider this object. So therefore if I consider capital F of gamma t, this will make sense, right? This is a very nice functions because compositions of two functions, a capital F composed with gamma, because if t runs from closed interval a to b, my gamma of t runs over my contour c, and capital F is defined, capital F, if I say that capital, what is my capital F? Capital F is also a function from D to C. So that means this is also defined in D. In particular, this is also defined on C. So therefore, capital F of gamma t makes sense. Okay. And capital F is differentiable because small f possesses an antiderivative. That means capital F is differentiable. Small what can I say about gamma? Gamma is the parameterizations of my contour. Now contour is means piecewise smooth curve. In fact, it's a smooth curve. Okay, so therefore small gamma is differentiable. So therefore this is differentiable. This is differentiable. Therefore f composition gamma, this function is a differentiable functions. Now if I calculate the derivative of these functions f of gamma t, then what will happen? By chain rule it says that this should be capital F prime of gamma t, then gamma prime of t, by chain rule, okay. But what is capital F prime of gamma t? Because small f possesses antiderivative, that means capital F prime of gamma t is small f of gamma t, so therefore this is small f of gamma t times gamma prime t, right? So this is, that means ddt of f of gamma t, just by chain rule I can have, this is nothing but capital F prime of gamma t times what is called gamma prime t, and capital F prime of gamma t is exactly equal to small f of gamma t, because capital F prime is equal to f, because small f possesses antiderivative. So therefore this is exactly equal to this. So therefore now this is the definitions. So this is the contour integrations. By definition this is exactly equal to this one. Then using chain rule I will have, this is same as integrations a to b, the derivative of capital F composed gamma, and capital F compositions gamma, it's a differentiable functions. So therefore by fundamental theorem in real analysis, this is exactly equal to capital F at the point value of the functions at the end point. That means it is exactly equal to capital F of gamma a minus capital F of gamma b, right? Because this is by fundamental theorem of integral calculus. So fundamental, that means that means you can say that this is same as integrations a to b capital F composed gamma prime t dt. Then by fundamental theorem, this is capital F of gamma A minus capital F of gamma B. But what is capital F of gamma A? That means gamma of A is nothing but capital F of Z2 minus capital F of Z1, because gamma A, you see, gamma of A is Z1 and gamma B is Z2, because gamma is a parameterization of my contour starting from the point Z1 ending at the point Z2. Since this is a parameterization, so therefore gamma of A is equal to Z1, gamma of B is equal to Z2. So therefore what we have observed is that the corresponding contour integrations, if I calculate in this way, it will have the value capital F of Z2 minus capital F of Z1. Now you can guess what is capital F. Capital F is the primitive. If small f possesses a primitive or antiderivative capital F, so capital F is a primitive is given, Z1, Z2 fixed. So therefore whatever contour I can take, the value of the contour integrations is nothing but the value of my antiderivative at Z2 minus value of my antiderivative at Z1, right? So therefore the right hand side, it is independent of the choice of the contour. It depends only on the antiderivative capital F and only at the point Z1 and Z2. So therefore whatever contour I can take, value the right hand side will be independent of the choice of the contour. So therefore, and this is exactly the statement. So therefore if small f possesses a antiderivative or primitive, then the corresponding contour integrations or line integral exists and it will give you the same value. And what is the value? Capital F of Z2 minus capital F of Z1. Now from this formula, one easy note you can have it. It says that this integration, contour integration is 0 if C is a closed contour. Now if C is a closed contour means what? That means if C has a parameterization gamma, that means gamma of A should be exactly equal to gamma of B. And what is gamma of A and gamma of B? That means Z1 is equal to Z2. Now if Z1 is equal to Z2, then what is the value? Capital F Z2 minus capital F Z1. This is 0. So therefore this is a consequence of that. So if I take a contour C starting from Z1 ending at Z2, so the corresponding contour integrations, whatever contour I can take, as long as it starts from the point Z1 end at the point Z2, it is independent of the choice of your contour, the corresponding contour integrations or line integrations. And if I take a closed contour, that means Z1 is exactly equal to Z2, that means this value is 0. So therefore it is very nice that if a function f, if it possesses antiderivative or primitive, then in the domain, if I take any 2 points Z1, Z2, then the corresponding contour integrations, it's independent of the choice of the contour. Now what is the advantage of this kind of things? Now you will see, so for example, you just think about real analysis. Now real analysis, I can make sense of this kind of integrations, like a to b fx dx, right? Because if I have an interval a to b fx dx, right? So this is the Riemann integrations you know. Now you can ask, now I have say complex valued functions over complex domain, right? So suppose you have a domain D and you have a complex valued functions and take 2 points Z1 and Z2. Now you can ask, can I make sense of this kind of integration, say Z1 to Z2 f of z dz? That's, you can ask it. But then if you just compare with real analysis, you can say that, sir, in real analysis there is a ordering between A and B. But if there is no ordering in the complex number, we know that there is no ordering between, then I cannot compare two complex numbers. I cannot say that Z1 is lesser equal to Z2 or Z1 is greater equal to. No, I cannot say that. There is no ordering. That is the difference between real number and complex number. So in the real number, if A to B means A is the left hand side, B is the right hand side. So therefore, I am just calculating from A to B fx dx. Now, whenever you are saying Z1 to Z2, now Z1, Z2 are two distinct complex numbers. So but there is no ordering. So what is the meaning of Z1 to Z2 fz dz? Then I will say that, well, no problem, you can take this one Z1, you can take this is Z2, right, 2 points. Now what I will say that, okay, this integrations I am defining it, take a contour C, and this is nothing but the corresponding contour integrations I have already discussed, right, that I already discussed. If I have 2 points, if I take a contour, you can define that this object, this is a notation which is nothing but the value of these contour integrations. Then one can easily ask, sir, if I take another contour, say C twiddle, starting from Z1 ending at Z2, then let me just discuss once again. So suppose you have this domain and I have 2 points Z1 and Z2. So now I want to make sense of integrations Z1 to Z2 fz dz. That's my plan. Because you know the integrations A to B fx dx. Similar kind of object I would like to give meaning in the context of complex setting. So my point is that, okay, I can say that, okay, this is a notation. I am saying that take a contour C. I am saying that this is nothing but integration C fz dz. Okay, you just define in this way. Then one can easily ask, okay, instead of this contour, if I take this contour, say C2 del, again it is starting from Z1 ending at Z2. Can I give the meaning in this way, C2 del? That is a kind of right to ask, right? If I take a different contour, can I give this definition as in this way? Well, so the question is, that means if I change another contour, can I give? So that means there are plenty of contours, right? Joining at Z1, ending at Z2. Which contour I should take to give the definitions of this object? Now the point is, the if I somehow convince you, it doesn't matter whatever contour you can take, as long as it starts from Z1 and end at Z2, all the corresponding contour integrations is independent of the choice of contour. That means it will give you the same value. So therefore, in that case, I can easily say that, yes, look, that now I am defining is nothing but take some contour and the corresponding contour integrations. Because whatever contour we will take, it will give the same value. That means I need the path independency joining Z1 and Z2. If these things happen, then I can have this kind of meaning of this kind of symbol Z1 to Z2. Now this theorem, it ensures you this kind of definitions. This theorem says that, yes, if my small functions possesses an antiderivative, then the corresponding contour integrations, if I take a contour starting from Z1 ending at Z2, it is independent of the choice of the contour. So therefore, I can have the meaning of this kind of object, integration Z1 to Z2 fz dz, though there is no ordering in between Z1 to Z2. So the definition is that whenever I will say this kind of object Z1 to Z2 fz dz, I will say that this is nothing but, by my definitions, take some contour Z1 to Z2 and calculate this kind of contour integrations. And you do not worry, or do not kind of worry about the contour, which contour I should take, because whatever contour you can take, as long as it starts from Z1 and end at Z2, you will give the same value. So therefore, I can, now this is independent of the choice of the contour, so therefore definition is perfectly alright. So therefore, you can make sense of this kind of integrations. In other words, like for examples, you can make sense of this kind of integrations, like earlier you will have in real analysis a2x ft dt, right? And if I define is capital Fx, then what is the kind of fundamental theorem? Capital F prime of x is nothing but fx. Of course, some kind of continuity I need on f. There also I can define, say, some fixed complex number, say w to z, what is called? Yeah, so fz or z0 to z, fz dz, something like that I can define, okay? Or you can say that this should be z0 to z fw dw, okay? And I am defining this as capital F of z. Z0 is fixed. And what is the meaning of this kind of integrations? As I said, take some contour starting from z0 to z, and this is the corresponding contour integrations, right? That is perfectly all right. And but of course, you have to be very careful that it should be independent of the choice of the contour starting from Z0 ending at Z. Okay. Then you will have this kind of indefinite integrations. You will have this kind of indefinite integrations. Then you can talk about whether this capital F, whether it is differentiable, and if it is so, whether the derivative is exactly equal to small f, like in the real case. And in the next slide, we will have this kind of observation. In after 2-3 slides, you will see. Okay, so that is one of the advantage of having an antiderivative of a given function small f. I can make sense of this kind of integrations. That is the advantage. So for example, like antiderivatives. So whatever I have explained, I have written it. Look, whenever such kind of capital F exists, that means these contour integrations, now I can write, right? Z1 to Z2 fz dz. Now there should not be any confusions. So whenever I am writing this Z1 to Z2 fz dz, then this is nothing but the corresponding contour integrations. And what is my contour? Take some contour. It starts from Z1, end at Z2. So you do not worry about which contour I should take, because it is independent of the choice of the contour, because my function small f possesses antiderivative capital F. So therefore this is same as integration Z1 to Z2 f prime of z dz, and therefore you will have capital F of Z1 minus capital F of Z2, like the fundamental theorem. So that's, I have exactly proved it, right? So integration C fz dz, which is capital F of Z2 minus capital F of Z1, and this is same as, you can have it, integration Z1 to Z2 fz dz. Okay, so perfectly all right. Of course, you have to be very careful. Each time I am assuming that my function small f possesses antiderivative or primitive. If these things happen, then this kind of integrations or this kind of symbol makes sense, and you can have the value of these integrations, which is nothing but these contour integrations, and value is capital F of Z1 minus capital F of Z2. So one example I have just discussed. So for example, if I calculate integration Z1 to Z2 Z squared dz, what will be the value? So that means first you just ensure that whether your integrand, that means Z square, possesses an antiderivative or not, and you can easily check that. Yes, if capital F of Z is 1 by 3 what is called ZQ, right, then what is the capital F derivative? This is 3Z square by 3, that means Z square, and this is exactly equal to your integrand small f. So therefore this object, if I denote it as F of Z, it possesses antiderivative. So therefore by definition this object Z1 to Z2 Z square dz, which is same as integration Z1 to Z2, it possesses antiderivative, that means capital F prime of Z dz, and then by you can think about as a, like the earlier slides I have discussed, the value is nothing but capital F of what is called Z1 minus capital F of Z1 minus Z2 or Z2 minus Z1. Let me just see. I think this is Z2 minus Z1. Yes, Z2 minus Z1. Okay. So this should be, you can say that this is Z2. This is Z2 and this is Z1. Okay. So therefore this is nothing but Z2 minus Z1, and what is that? That means this is 1 by 3 Z2 Z2Q minus 1 by 3 Z1Q, and which is nothing but this one. Okay. Similarly, you can calculate that minus I pi to I pi cosine of Z dz, which is same because cosine possesses antiderivative. What is the antiderivative? Sine. Okay. So therefore by this formula you can have this value of this one. Similarly, you can value of this 1 by Z starting from minus I to I, that also possesses antiderivative. That means that is nothing but the principal logarithm capital log, and this is, that means the value of capital log at I minus this one, and if I just calculate the value it will end up which is I pi. So this is the advantage of a functions possesses antiderivative, then you can easily calculate this kind of what is called integrations, definite integrations, provided it makes sense in this way. So that means if I say that Z1 to Z2 fz dz, that means this is a symbol you can think about. This is a symbol you can think about. So the meaning of this integration, that means you can take some contour starting from Z1 ending at Z2 and calculate the corresponding contour integrations. And since it possesses antiderivative, it is independent of the choice of the contour. So you just calculate these contour integrations, and in my last slides I have calculated, and this is nothing but the value of your antiderivative capital F at Z2 minus value of your antiderivative capital F at Z1. Okay, this is the formula. Okay, this is another kind of examples I have explained. Okay, same thing, the functions 1 by Z to the n is greater than 1. It is a continuous function on C star. C star means what? This is actually C minus the origin, because it is 1 by Z, so 0 will have a singularity. So thus the integral of the above functions on any contour joining non-zero complex number Z1, Z2 not possessing through origin is given by this, which is same as this. That means it says that if I take a complex plane except the origin, if I take out that one, then this function f of z 1 by z to the power n, it is a very nice function, it is a continuous functions, and on that domain capital F of z, okay, because I need to write, so capital F prime of z should be 1 by z to the power n, right? So that means this function possesses antiderivative. What is my capital F? So capital F, of course, it has to deal with the 1 by z to the power n minus 1, that's the only point. Okay, so therefore 1 by z to the power n minus 1. Okay, so if I have it, then I think it should be a 1 by n minus 1 factor will be there. Okay, maybe. Okay, so if I calculate the capital F derivative, then what will happen? This should be 1 by n minus 1, keep as it is, and this should be so this should be 1 minus n, then 1 by z to the n. Okay, and this will get cancelled. That means up to a minus sign, that will be minus sign. If I have minus sign, that means it is. So this is the things object. Okay, so therefore since it will have a possesses an antiderivative, then the integration z1 to z2 1 by z to the n dz, which is same as integration z1 to z2 capital F prime z dz, and this is same as capital F of Z2 minus capital F of Z1. So that's kind of it. So therefore, if I do that one, so it will have this kind of object. So 1 by Z2 to the power n minus 1 minus 1 by Z1 to the power n minus 1. Maybe this factor you can just check out. I think this should be 1 by, I think, okay. Because of my formula, it should be 1 by. Check it, okay. So in particular, this becomes 0 if C is any closed curve not passing through. So that means if I take simple closed curve, it starts from here and this one, because the corresponding value of f of Z2, so that means Z2 is equal to Z1, that means the difference, if Z2 is equal to Z1 is equal to Z, that means this difference is 0. So that's exactly I have written. So this becomes 0 whenever C is any closed curve. Of course, you have to be very careful not passing through the origin. Of course, and because I am considering the domain C minus origin, okay, so it's perfectly alright. So therefore, as long as your functions, whatever functions you can take, here I am considering the functions f of z is equal to 1 by z to the n, so it possesses an antiderivative, and therefore by the theorem, so the corresponding integrations like z1 to z2 dz divided by z to the power n makes sense, and this I can, by the formula, that this is nothing but the value of this integration is nothing but value of my antiderivative at the point z2 minus value of my antiderivative at the point z1. That's it. So this is the way you can calculate using if your function possesses an antiderivative. Okay. Okay. So I think that's okay. So now I have discussed till now the what is called the existence of antiderivative, right? So what is the definitions of antiderivative I have discussed, and if suppose if you have a functions f and if it possesses an antiderivative, then what advantage I will get? So one advantage is that if I have a functions f defined on my domain D, and suppose small f, my function small f possesses an antiderivative, say capital F or primitive capital F, then the observations I have it is that if I take 2 points z1, z2 in my domain D, then whatever contour I can take starting from z1 ending at z2, the corresponding contour integrations will give you the same value. That means my contour integrations from z1 to z2, it is independent of the choice of the contour. So that's what I have discussed till now. Now in my next lecture, I will talk about when can I say that my function possesses antiderivative. If antiderivative exists, then I have some conclusions. The next part is that when I can ensure that yes, look, if these things happen, then your functions f always possesses antiderivative. So that's kind of theorem, if I have it and if I combine it, then I will say that if your function satisfies this kind of things, then if I take 2 points z1, z2 in my domain, then the corresponding contour integration is independent of the choice of the contour, starting from the point z1 and ending at the point z2. So therefore, in my next lecture, I will give you some conditions. So that means if I have my function is nice, if my function is defined on some domain, it is also nice, then I can say that yes, if these things happen, then your functions or my function small f always possesses antiderivative. I think I will start with those kind of concept in my next lecture. I think I should stop here. Thank you.